Hello everyone, I'm Shengyu, a PhD candidate at the UCAS. It's a great pleasure to be here to present our work. My presentation today consists of the following parts. First, I will briefly introduce the basic concepts of fully homomorphic encryption, as well as some SOTA FHE schemes. Then, I will explain the motivation behind our work. After that, I will go into details about the design of our FHE Accelerator. Finally, I will show the results of our experimental evaluation. FHE is an emerging cryptographic technology that allows computations to be performed directly on encrypted data without decrypting it. However, this powerful capability comes with a significant computational cost. There are two main sources of this overhead. First, compared to plaintext, ciphertext can be thousands of times larger in terms of both storage and computation. Second, to ensure that the ciphertext remains decryptable after computation, FHE systems require additional complex operations such as bootstrapping, which is used to reduce the accumulated noise during computation. To gain a deeper understanding of the computational bottleneck in the FHE applications, we conducted a hierarchical classification analysis of FHE operation. Our analysis reveals that homomorphic multiplication and homomorphic rotation plays crucial role in FHE computation. They are also the core components of the bootstrapping process. As a result, key switching operation dominates the both multiplication and rotation, making them the crucial piece for improving the performance of FHE applications. Next, I will briefly introduce two widely used and efficiency key switching optimization, the KRSS algorithm and the hoisting method. KRSS method was first proposed by Korean researchers. Unlike the traditional hybrid method, the KRSS approach first maps the leaps into the new modular space called RT, and then performs the multiplication and the corresponding key. Compared to previous schemes, KRSS effectively reduced the number of entity-related computation, but it introduced a higher computational cost in key multiplication. In addition, there is another widely adapted method known as hoisting. This method is designed to focus on where the same ciphertext is routed multiple times at different positions. The core idea is to use the output of the model up step in the key switching, thereby reducing the expensive entity computation. More specifically, the hoisting technique first performs one model up operation on the ciphertext, and then carries out a multiple rotation for different positions, each followed by a multiplication with the corresponding key. Next, I will introduce the motivation behind our work, building up the background we have just discussed. First, we observed that the ciphertext level changes continuously during the execution of FHE applications. However, the performance advantages of different key switching algorithms vary depending on their ciphertext level. For example, in centralized, the KRSS algorithm performs better, while in others, the hybrid method delivers superior performance. In addition, when the hoisting technique is applied, the performance gap between different key switching methods also shifts. This leads us to an important insight. There is room for optimization by dynamically setting the optimal key switching method based on the current ciphertext level and whether hoisting is being used. At the same time, this approach introduces a significant challenge. Both KRSS and hoisting require additional key data, which greatly increases the storage overhead for the keys. This means that in designing an accelerator system, we must not only focus on improving computational performance, but also carefully consider the on-chip memory limitation. and seek a balance between computation and storage. In addition, we observed that the KRSS algorithm, in order to reduce the number of entity operations, typically require a larger word size models, such as 60-bit precision. In contrast, traditional ciphertext operations and the hybrid key switching method can usually be performed with just 36-bit precision. However, higher bit width not only results in great area and power consumption, but also reduce parallelism in low precision computation scenario. Based on its observations, we believe it is necessary to design a computing unit that can flexible supporting multi-precision configuration, ensuring full functionality for high-precision tasks, with an increase in parallelism and overall performance in low-precision scenario. Therefore, based on the motivation and the design opportunities we have just discussed, I will now present the details of our accelerator system design. First, I will introduce the software design for our FHE acceleration system. Our software system consists of two modules, Ether and Homomorphic. The Ether module runs on the silent side and is responsible for analyzing the applications and execution patterns and selecting the most suitable key switching method for each computational context. During the analysis phase, Ether scans all H-root and H-mort operations in the application's execution flow. Ether estimates the number of modular multiplication required, and Ether and then analyze whether hoisting is used and evaluate the memory requirements. Finally, stores this information in a structure called the MCT. Based on the statistic recorded in the MCT, the system performs a series of sliding steps to determine the most suitable key switching algorithm. First, it eliminates any method whose key size exceeds the on-chip memory capacity, and then it removes the method whose key transfer latency exceeds the pipeline scheduling window, and avoid two potential pipeline stall. And then it will slide the minimal execution time with the configuration. Either in the key management model deployed on the server side, its primary role is to prepare the key data for the accelerator. During execution, Homomorphic processes the FHE computation graph to locate all operations that involve key switching. And then, based on the configuration file provided by the Ether silent, Homomorphic sets the suitable key host ID and key switching method, allowing it to identify and dispatch the required keys. Then, based on the to support the fast access and scheduling, Homomorphic maintains a history table that records for each ciphertext level the corresponding host ID and key switching method. In terms of key organization and storage, Homomorphic also performs batch reorganization of keys based on the accelerator's input data pattern to better meet its throughput requirements. Additionally, Homomorphic also provides a key prevention behavior to meet the to support the FHE accelerator execution. In addition to software level support, flexible accelerator both the KRSS and hybrid methods also require hardware level adaptability to support mixed precision computation. Based on our previous motivation analysis, we designed a tunable-bit with multiplier, which is capable of dynamically switching between 36-bit and 60-bit precision at runtime. In 36-bit model, we divided each input to sub-blocks, a higher part and a lower part. They are processed in parallel by two multipliers, double the throughput for 36 operations. In 60-bit model, we also split the input into two parts, the lower 36 bits and the upper 24 bits. They are then combined with the multiplier to complete a full 60-bit precision computation. With this design, our TBM model not only adapts dynamically to different precision requirements, but also enhances parallelism and throughput in low precision scenario, meeting the performance optimization needs of different key switching methods. Next, I will introduce the overall architecture of our proposed accelerator. Faster accelerator is composed of 4 parallel clusters. Each cluster contains several key functional modules, including NTT unit, base conversion unit, auto unit, key multiplication unit, and AEM unit. The interim accelerator fills a total of 1,024 computation lane. Each line integrates our TBM model as its fundamental symmetric engine. Thanks to the flexibility of the TBM, FAST is able to dynamically support different precision models, which allows it to efficiently balance the performance and hardware resource usage when executing both the KRSS and hybrid key switching algorithm. The NTTU is a crucial computational model within the FAST accelerator. In our design, we build up the 10-step NTT approach. Specifically, the NTT process is divided in 2 stages. In the first stage, we apply the classical full-step NTT algorithm to perform transformation along the column direction. This followed by a matrix transformation operation. Then, in the second stage, we perform another round of full-step NTT in the row direction, completing the full NTT operation. Unlike the sharp, FAST replaces the traditional multiplier in the NTTU with our customer-designed TBM models. This modification brings some major benefits. When executing 36-bit precision NTT operations required by the hybrid key switching algorithm, the TBM enables higher parallelism as a result. The overall NTT parallelism increased from 256 to 512 lanes, boosting the throughput of the NTT operation. Next, I will present the evaluation results through our co-design software and hardware optimizations. This is my area results. Our area increased 2 times in logic area, and looking at the area breakdown, the on-chip memory takes up the larger partition, accounting for 43.7% of the total area. In terms of performance, the faster accelerator achieves an average speed up of 1.8 times across multiple applications. And looking at the individual operator, the T-Mart operation achieves 2.4 times speed up. To conclude, our work lists the following takeaways. First, the design of FHE Accelerator must adapt to the advancement of algorithms. Recent optimizations such as KRSS and hoisting show great promise in reducing computational overhead, but they also impose high demands on hardware resources. Second, pure hardware scaling is not enough to unleash the potential of its algorithms. A co-design approach is needed, one that dynamically balances computation, bandwidth, and on-chip memory resource to achieve real performance gains. Finally, this work presents the first hardware-level support for multiple key switching algorithms and tunable precision computation, paired with software statistical scheduling and configuration management. Although this introduces around 1.6 times increase in total area, we demonstrate that through architectural parallelism and data flow-aware scheduling, we can achieve performance improvements across FHE workloads. Okay, this is all my presentation. Thank you for your attention.